Hello, hello. Hi guys, you're welcome to God Academy. And in this lesson, I'll be taking you through double integrals. So we've ended differentials, okay? In our previous lessons, we did differentials, partial derivatives. Then we came to do the applications of what partial derivatives. So we continue in this session with double integrals. So what do we mean by double integrals? Now we are doing functions of several variables. Is that not it? So meaning you are dealing with a function of x and y or a function of x, y, and z. If you are differentiating functions like this, we introduce what we call double integrals, meaning that one integral is not enough. Okay. So we say that if you have a function like this, you go double integral for a function f of x, okay, over a region R. That is the definition, dx. Sorry, a function f of xy. So a function f of xy over a region R, right? Dx, dy. Or you can have, so now since you are doing double integrals, you are only going to stick with xy, okay? So this is what we are going to do in triple integrals. So we have double and triple. Triple is when you're dealing with x, y, and z, okay? So for now, let me get rid of the triple. So with double integrals, the region of your integration is what matters. That's the whole idea. Okay. The region of integration is what matters. Now let's see our plane here. Z, X, and Y. Okay. Let's see this here. Then if I'm doing an integral over a plane, which is my region, okay. Now you realize that rectangular region. Okay, that is the basic double integral you ever get. R is defined as AB cross CD. It's not necessarily cross. So you are trying to say that we have two separate boundaries. We have one for AB, which is going to deal for the X. We have CD going to deal for what? The Y boundaries. Over our integral R, right, of f of xy, the A. So your area, or the A here, is simply going to be what? The X times the what? The Y. I don't know if you get it. So this is the definition of double integral. We have a function of xy and we are integrating it two times over a certain region where we have the A over the area, and the area is given as what? The X times the Y, like area, length times breadth, right? Looking at the rectangular region, which you can see nicely here. Okay. Now we have what we call iterated, right, integral from C to D, f of x y dx dy. Okay, that is a typical one of a double integral. That's what I miss. So now let's talk about the Fibonacci theorem, then let's solve an example for you to appreciate. Okay, so now, okay, so for the Fibonacci theorem, what Fibonacci theorem is saying is that you know that once you are dealing with double integrals, so let me use my blue. Once we are dealing with double integrals, we're surely going to have this problem here. So if I have my double integrals of R for x, y, dA, right, being equal to integral AB, integral C, integral, then we have the outer integral. So the result of the inner integral, then we have the outer integral. So the result of the inner integral gives us what? The next function for us to proceed to find the outer integral. And please take note, always your outer integral should be should have finite boundaries. Okay, mostly you appreciate that as we move on. So let's summarize. For Fibonacci theorem, we are trying to say that your rectangular region can give us two iterated integrals. Either you differentiate the y first before, either you integrate the y dx or the x dy, and they will swap your boundaries accordingly. It's very, very, very important. Okay, it's very important. Having learned this, let's solve some examples to warm up. So our first example: find the double integral over the region R for the function 6xy squared the A, where R, which is the region, is given as 2 comma 4 plus 1 comma 2. So let's solve this problem. So our first double integral problem. Okay, so with this double integral, we've been given the region R to be 2 4. Please take note, the first one is for x, the first one for y, mostly when they give it to you for any rectangular coordinate. Okay, so we simply have to come to our equation, then we will distribute. Okay, so you have to choose which one do you want to do first. If you want to do x first, then you should what? Put x. You see, we have the inner and the outer. Inner is done first, so the inner is what comes first. If you want to do x as inner, then it will come inside. Okay, so let's do x as inner and y as outer. Y as outer, I'll have 1 2 because that's the what coordinate here. X as inner, I'll have 2 4. My function 6xy squared. Then since x is my inner, I'll have the x, the y. As simple as that. Take note, if you miss it and go and do the y dx, you are wrong. So this then becomes integral from 1 to 2, right? Then doing your inner, what do you get? I'm integrating this with respect to x. Take note, that's my inner integral with respect to x. With respect to x, y becomes a constant. It will step out, y squared. Integral 6x, okay? 2 to 4, as simple as that. The x, the y. Once you have this, then you know that becomes what? S squared over 2, right? Cancel, getting 3x squared. So I'll have my answer to be integral 1 to 2 y squared multiplying 3x squared. Then my boundaries, please, you have to put in your boundary values. It's very important. It's this one is what we call a definite integral. Okay, so you have your 2 and your 4 applied, everything inside, then your dy outside. Okay, so with this, what do? You have integral from 1 to 2, then my y squared is out, right? So my y squared Then what happens here? I'll put 4 inside, I get 16. Then 16 times 3 is what? 48 minus, I'll put 2, I'll get what? 4. 4 times 3, 12 dy. The answer becomes 1 to 2. Then this will give me 36 y squared dy. So at this point, to find the integral, what do I get? You just simply what? Add 1, 3. So you get y cubed. So I get 12y cubed. Is that not it? 12y cubed. Then from 1 to 2. So I have 12, open bracket, 2 cube minus 1 cube. Obviously going to be what? 8 minus 1, which is 7, right? So 712, which is what? 84 as our answer for the double integral. So this is the simplest problem you can ever get over rectangular region. It's actually the simplest, as I said, very, very simple. Okay, it's actually the simplest that you can ever get. Let's solve the second problem. So I have my integral here, then I have my region R, okay, 2x minus 4y cubed dA, where my R is simply going to give me negative 5, 4 cross 0 to 3. So this one is also similar. Which one do you do first? We can do y first and x as outer. So let's try that. So using x as our outer, negative 5, 4 will come out. Then our inner 0, 3, meaning you do y first, right? So doing y first, we are simply going to have the function 2x minus 3y. Sorry, I've written a different function. We are simply going to have 2x minus 4y cubed. Okay, 2x minus 4y cubed. Then I'll have my, so I have this 0 to 3, negative 5, 4. Okay, so since my y is in the inner, I'll have dy dx. Okay, you appreciate the order. Now it seems all of them are numbers, so it's easier to choose the order you like, and each of them, any of them will work. So now let's do the inner with respect to y. What are you getting? With the inner, I'm going to have here with respect to y, I'll get 2xy. Get it? 2xy. Then minus this one, I'm going to get y to the power 4. Please, at this point, you've done integration in calculus 1. I'm not going to stress on the integration. And then at this point, I'll put 0 to 3. Then all this thing, the x, my outer integral will come negative 5, 4. As simple as that. So integral negative 5 to 4. Then this one, when I put 3 inside, I'm getting what? 3 times 0. Here will be 0, right? And I'll get negative 3 to the power 4. So I'll have negative 3 to the power 4, right? Negative 3 to the power 4. Oh, sorry. I'm doing for only the x, only for y, because we first different integrated with respect to y. So wherever I see y, I'll put 3. So I have 2x multiplying 3 minus 0. Take notes. Minus 3 to the power 4 minus 0 to the power 4. Then the x. So at this point, what do I get? At this point, I simply get integral from negative 5 to 4. This is 3, so making 6x. Okay, 6x. Then this one is 3 to the power 4 is what? That's going to give us 81, right? Yes, so 81. So minus 81, everything dx. Let me see. So once we have this, we are now going to integrate with respect to x, right? So this will give us x squared. So 3x squared minus 81x. Is that not it? Then you put in your negative 5, then 4. So put in your negative 5, 3, 4 squared, right? 4 squared minus 81 multiplying 4 minus the expression 3 negative 5 squared minus 81 multiplying negative 5. So just enter this into your calculator, and what answer are you getting? This is a simple, so 3 times 16. Okay, let me do the inner, right? We have 16 minus 4 times 84. That's minus 68, right? Times 3. Negative 204. So negative 204 minus. Now 5, negative 5 squared is 25, right? So 25 times 3 is 5. 75 plus 40. That's 115. So 115. So what are you getting? So neg 319. Your answer. So this is all for rectangular region. Rectangular region. Let's go to another interesting section of double integrals. We call them special cases. Special cases. Special cases. So for special cases, we have one. We have one to be six. Sorry. So let me explain the special case. If I have a double integral over a region R for the function f of x, y, the a, right, is equal to an integral. Now, the difference is that if you have any function which can be splitted into a group of functions, so that one will be a function of f of x and the other will be a function of f of y, then this theorem holds. So now, assuming that our function f of x is f of x multiplying h of y, I don't know if you are getting it, the a. Assuming that you can, the function that have been given to you, you can group the x alone times the y alone, then you can break it into two separate functions. And the rule is saying that once you can do that, then your integral will be so simple. How would it be? To simply be integral. So let me write as integral c to d, integral a to b for the function g of x multiplying h of y. You let me use h of y, h of x, right? The x dy, okay, the x dy. This is the same as having integral from c to d. So c to d is for what? It's for my y. Then I'll take my y function, h of y dy times integral from a to b for what? My g of x dx. As simple as that. And your answer will be perfectly right. That's the whole trick. So the trick is saying that you can break your function, which now can be expressed into a function of x times a function of y, though it's a single function. Then after you intentionally spread your region, so your x will go for the x part, the y will go for the y part. Let's solve an example so that you understand this. So an example here, I have double integral of x cosine squared of y dA, where my r, so my r is here, where my region is simply a rectangular region, negative 2 3 from 0 pi on 2, as simple as that. Now you can clearly see that this function that we have, which is x whole squared y, I can break it into two, as a function of x, which is equal to f of x, and a function of y, h of y, which is what? Cos squared y. Right? You can see this clearly. Therefore, my answer is so simple. When I take my x part, which is f of x, so integral f of x, which is what? My x. What's my limit for x? Negative 2 to 3. I'll separate it, my dx, as simple as that. The answer I'll get will multiply my integral y, which is what? 0 to pi on 2. I'll separate it. Then I have what? Cos squared of what? Of y dy, as simple as that. So you just separate it into two. If you don't do it this way, I think it's going to be difficult for your integration, okay? So these are special cases. Sometimes you have to open your eyes so that you don't skip. Now, let's do our integral. This is x squared over 2. I'll have negative 2 and 3, right? My answer will multiply now. Now, if you have cos squared, you know that cos squared is the same as what? Cos squared theta is the same as 1 plus what? Cos, 1 plus cos 2 theta over 2. Is that not it? As simple as that. So let's replace it. So as usual, integral, and this is so now I'll replace the theta with y. So integral from 0 to pi on 2 whole squared y then becomes my 1 plus cosine 2 theta all over 2 dy. When I put 3, I'll get 8 over 2, which is 4, right? So 4 minus the expression. When I put negative 2, I'll get 4 over 2, which is what? 2. And the answer is going to give me what? 2 for this. So 2 times. Now this expression, what do I get? So for this expression, what do I get? So now, When I have this, I'm going to have here, I'll put my half. Your 1 out of 2 should come out of the integral. Integral 0 to pi on 2. I'll have multiplying 1 plus cos 2 theta dy. This integral, we've done it before. I think I can even put the answer there straight away. So here, what do I get? I will integrate this with respect to y. I get y. Oh, sorry, this is not theta. Sorry, you have to get rid of the theta and make it y. We are not dealing with, so make it just y. So 2y, it becomes 2y. So I get my y plus, when I integrate this, I'm going to get sine, so 2, sorry, 1 out of 2. 1 out of 2 sine 2y, like this. Okay, 1 out of 2 sine 2y. Then I'll have this nicely done. Okay, then I have my 0 towards pi on 2. Remember, we have 1 out of 2 here. Okay, it's not gone. Okay, so now you're going to have y out of 2 plus 1 out of 4. The expression sine 2y from 0 to pi on 2, right? Multiplying our expression that we had here. 2. So with this expression alone, what do I do? When I put my pi on 2, I'm going to get pi on 4 for the first part. Minus 0. 0 make it everything 0. So pi on 4. Then plus, when I come here to, I'll put my pi on 2. So 2 times pi on 2 become pi. What is sine pi? That is sine 180. Sine 180, which is 0. Okay, sine 180 is what? Is 0. Okay, so sine 180 is 0. So minus the 0 minus, when I put actually 0 inside, I get sine 0 to be what? 1. And that'll give me what? 1 over 4. I'm going to get pi on 4 minus 1 out of 4, which is this as pi minus 1 over 4. And what do we get? You have 2 outside, right? So 2 times this, we are going to get pi minus 1 all over 2. As simple as that. I believe you've gotten the idea or what I'm trying to draw your mind to. Okay. So now we've done rectangular, we have done special case of a rectangular. Then what's next? What's next? So we are going to what we call integral, double integral, double integral over general region. General region. So for double integral over general region, what do we mean? It was so nice when you were solving the integral and it was rectangular. Please, it's not always rectangular, okay? There are cases where your region R is going to be any region. The word any region here means that your region R can be x squared, can be y cubed, root of y. They are all regions. So a case will come where I'll give you your limit to be what? X squared, comma y cubed, and I'll give you 1 to be 2, 1. How do we do this? Another case for our general region is where you have to reverse your order. What is the need and when do we reverse order? Why do you have to reverse order? So let's go through this thoroughly and observe carefully. So generally, double integral over what? General region is defined as double integral d for my function of x, y, dA. Okay, where d is any region you can think about. I'm going to draw two regions here. I have my x and y. So this is my y, this is my x. Okay, so I have something like this. Then I have something like this. Oh no. So this is my x. Good. So let me shade my region. So region on top, this is one curve, this is one curve. We want to find the integral. Okay, we want to find the integral over this double so one is a curve and that is a curve. And remember that these integrals are bounded. In our previous that is the rectangle, I realized that you saw a clear rectangle as a region. Here, what do we see? We're going to see four boundaries. One will be what? This curve itself. This curve itself is one boundary. This one is another boundary, boundary two. Then these are the third boundary and fourth boundary. That is the tips. So this gives us our R. Now, let me draw the other case. The other case too is the same thing. I have my Y, I have my X. This time, my curves are parallel. My curves are parallel to my X. So I'll have some. Oh, so, so with that in mind, now let me put. So I'm having something like this. So I'll trace this to my Y and I'll have my. This is now my function Y, which is equal to G of X. G1, my function Y, which is equal to G of X. This here is my function X, which is equal to H2 of Y. This is my function X, which is equal to H1 of Y. I want you to appreciate something here. There are two scenarios here, and these two scenarios will help us through our general region. We use these scenarios whenever you want to switch and whenever they give you integrals over some strange regions. Okay, you should be able to draw. At this point, you should be able to draw curves and you should be able to what? Define the boundaries as much as possible. As much as possible. For our first scenario, you can see that the curves are in the form y is equal to equation y is equal to, right? So this equation y is equal to is trying to tell us that our function here is in the sense of y. So whenever you have a function in the sense of y, they cut through this way. When you cut through this way, you realize that you have what do we say? Y is equal to, oh sorry, you cut through in parallel form. Okay, so here if we are to cut, you understand the cutting very soon. So when you cut through, whenever it's y equals it, you cut through in parallel towards your y-axis. Therefore, your function is going to start from the lower point, which is this, to this, with the boundaries a and b. So let's define. So therefore, our boundary d for this one is such that x comma y, a less than or equal towards x less than or equal to b, t1 of x less than or equal towards y less than or equal to g of what? X. As simple as that. This is for this region. So this is region D1. This is region. So this is D1 definition. So D2. So D2 is simply going to be the same XY, but this time I have my function switching, right? I have my H1 of X less than or equal to X less than or equal to H of what? X, right? Comma. I have C less than or equal to Y less than or equal to, as simple as that. So I have this. So once I have this position this way, then what's next? But here's the clear explanation. In this scenario, our functions are in the what? S is equal to, meaning that they are what? Parallel to what? Like, I mean, they are in the sense of the x. So in this case, we traverse through like this. We cut through in parallel to x. Here we cut through in parallel to y to get this. So here when you cut through in parallel to what? X, you start from x1 of hy to x, which is equal to h2 of y. Then your y limit then becomes what? Your c and your a and b. Here when you cut through y, your y part becomes function and your x becomes what? Known values. Here when you cut through x, your y part becomes known value and your x becomes what? Function. As simple as that. As simple as that. Okay, let's see some properties. So double integral over region D of a function xy plus a function g of xy a is given as double integral d a function xy plus double integral d a function g of xy a. This is trying to tell us that if you have two functions adding, you can find each, like you can just distribute, okay? Then you can also have, if you have integral c multiplying a function of xy where c is a constant, the a, just put your constant outside of your double integral, then simplify your xy a. Similarly, you can break your region into, so a situation where I have double integral of a region d of my function xy dA, this should be equal to my region d1 of xy dA plus region d2 of xy dA. So these are three fundamental properties of integrals you should know as you're about to solve over general region. Let's solve our first example. Is first example, double integral e to the power x over y a. Okay, then our d is defined as x comma y, 1 less than or equal to y less than or equal to 2, x greater than or equal to y less than or equal to y cube, like this. So let's solve this. To solve this, what do we get? Solve this expression. So this is d. Okay. So to solve this expression, we are going to have um so you know that this is your what y, um this is your y boundaries and this is your what x boundaries, are not it? So you have to just choose what you want to do as that. Please, whenever you are doing over general region, put the ones which has the known values outside. Please, that one is a must. Like you don't compromise. The one with the value, because you should end up getting a definite integral. So you should put 1, 2. So it is what from 1 to 2 of what the function. That will be our outer integral. Then the inner integral will be what from x. As it said, x is greater than or equal to y. So it's going to start from what? From y to what? Y cube. And the function is what? E to the power x over y. Since our y is outside, becomes dx dy. Let's simplify this. We are integrating this expression with respect to x. What do? You are going to divide by the coefficient of what? X over y. This expression, if you differentiate, the answer you get, then you divide it by the whole thing. Okay. When I differentiate, I get 1 over y. When I divide, I get e to the power y x. Okay. E to the power what? Y. Oh no, sorry. I get y e to the power x over y. Then I'll put my y cube inside. Okay. What do I get? When I put my y cube inside, I'll get y cube. Now remember that we integrated with respect to x. So wherever I see x, I'll put my y cube and y. So I have my y e to the power. I'll put my y cube over y minus y e to the power y over y. This gives me y e to the power y squared minus this gives me y e, as simple as that, to the power 1. Now this becomes my inner. So I'll have integral from 1 to 2 y e to the power y squared minus y e dy. As simple as that. So with that in mind, what do? We are going to integrate with respect to y. We apply the properties. Integral from 1 to 2 of the expression y e to the power y squared y minus integral from 1 to 2 of the expression y e to y. I just separated. So here what do? You use by what? By substitution. So you get 2y. All these stuff, we've done it in single variable. So this becomes of 1 out of 2 y e to the power what? Y squared from 1 to, okay, from 1 to, then you have minus this one to, remember that you are, this one is a constant, e is a constant, don't forget. It becomes y squared over 2, and I have my e, then 1 to 2. When I put 2, I'll get 1 out of 2 outside, 2e to the power 2 squared minus 1e to the power 1 squared minus 1 out of 2. I have 2. Let me make e out of 2 for the e is a constant. So 2 squared over 2 minus 1 squared over 2. So this is 2e to the power y squared. So become 2 squared. So 4. This 2 cancel this 2. No, I can't just say that. Okay. So this is minus e. So 2e to the power 4 minus e over 2 minus this gives over 2 is what? 2. 2 minus half is what? 2 minus half is simply 3 over 2. So e over 2 times 3 over 2. You simply get 2e to the power 4 over 2 minus 3e over 4. This one is simply computation, right? So you can simply press this. That is your answer. So let's solve one more example on general region. So on general region, let's see this problem. Double integral over the region 4xy minus y cubed dA. Okay. Now my region D is given as xy. Oh, sorry. My region D is given as, let's see the definition. D is the region bounded by y is equal to square root of x and y is equal to s cubed. Y is equal to square root of x and y is equal to s cubed. So see this problem. Find the double integral over region D for 4xy minus y cubed dA, where dA is dx over dy or dy over dx. You have to specify. Then D is a region bounded by y is equal to square root of x and y is equal to s cubed. As beautiful as that. Okay, as beautiful as that. Now we need our, boundaries. These are the boundaries they're giving you. The next thing to do is to draw. Have to draw this. If you have this, before you draw, remember that you can equate root x to what? S cubed. I'll say that s is equal to x to the power 6. I have x to the over x to the power 5 minus 1 equals 0. X is either 0 or 1. You draw our x-axis, you draw our y-axis. So from 0 towards 1. Then you come to y, the boundaries for y. Y is equal to root x. How do we draw? To draw y is equal to root x, you differentiate it and you find how it will be increasing. There's no need for you to plot it. Remember that if you have y is equal to x to the power half, when I differentiate, I'll get half x to the power negative half, right? The double integral will give me what? Negative, meaning that my function will be what? An increasing function. So this is y is equal to, let me use different colors. So my function will be an increasing function here, nicely. Then let's come to this one. When I differentiate it to it, I get 3x squared 6x. That will be positive. So you have a decreasing function. So it will come down like this. And this is the region that, this is our region of interest. So this is y is equal to root x. And this is what? Y is equal to s cubed. Nicely. And they should span over 0 to what? 1. That is how we graphically draw this. Okay. Once you draw this, now you can clearly see that our x is greater than or equal to what, 0, but less than or equal to 1, and our y is greater than or equal to what, root x. Sorry, before you see, they gave us y is equal to root x and y is equal to x cube without saying which one is bigger. But after drawing, we realize that this one has what, an increase and is decreasing, so it's going to be what, y is greater than x cube but less than equal to root x. Take note of the difference. Once you have this done, then you bring your integral. So my double integral, my outer will be 0 to 1, and that is for x. And my inner will be what? From x cube to root x. Oh, sorry. Good. Then I'll have my 4xy minus y cube. 4xy minus y cube. Then you have the a. Okay. Have the a. Now, since you know that our dx is the outer, we simply say that integral 0 to 1, our dA is defined as 4xy minus y cube dy x. As simple as that. So you integrate this with respect to y. What are you getting? You get 2xy squared. You should know, minus y to the power 4 over 4. You put in x cube, you put in root x. Okay. When I put in x cube, wherever I see y, I get 2. This will be x to the power 6. So 2x to the power 7 minus. Oh no, I have to put the bigger one first. When I put the bigger one, I'll get what? Y squared. So to be what? X. So get 2x squared minus this one, y to the power 4. You end up getting x squared over 4 minus the expression. When I put x cube, x cube give me what? X to the power 6. So 2x to the power 7 minus, when I put x here, x to the power what? 12 over 4. Good. What are you getting? 2x squared minus x squared over 4 minus 2x to the power 7 plus x to the power 12 over 4. Then integral from 0 to 1 dx. So here you are integrating everything with respect to x. So I have my 2 over 3 x cube minus plus 3, right? So x cube over 12 minus I add 8. X to the power 8 over 4. This 13 plus x to the power 13 over 50. You put in your 0 to 1. Get your answer. So that's how you solve problems with what? General regions. General region. You just draw and you simplify. Okay. Just draw and simplify. Let's do one more last thing here on double integrals. For integrals over polar region. Double integrals over polar region. Now, generally we know that double integrals over region are f of x, y, a. You have seen that the a is either equal to the x, y, or the y, the x. We can change this to a different variable using Jacobian. You learn Jacobian alongside. But for now, you accept the change like that, okay? For us to change variables, polar means what? Theta and what? R. You should know that polar coordinate is theta and what? R. There are some functions, if you are simplifying and you don't convert them to the polar region, I tell you, you struggle. It will be difficult. So we always convert. And even one reason why we do the integrals of our polar region is that sometimes the region R will be what? A circular disk. In a circular disk, how are you going to use X and Y? It's going to be difficult. Sometimes the region may not be a circular disk, but they will define a circle of radius this and that at the origin. Those stuff is when we use polar region. Okay. So using polar region, we end up changing our integral so that it becomes integral. And whenever you are doing polar region, remember that you have your new regions. Okay, you have your theta greater than um let's say theta 1, theta 2. Okay, theta 1, theta 2. I have my r greater than or equal to r greater than or equal to r2, r1. So my theta 1, theta 2. So always your theta is out. Please check the algorithm. Always theta is out, followed by your r1 and your r2. And you have r, let's say a function of r, right? Amen. Okay. So now one special thing about polar coordinate, that's integration in polar coordinate, which I want to get some beautiful examples. Okay, I think I'm not. So now when you talk about the polar coordinate, okay, one special thing is that our dA, the polar coordinate become r dr d theta. Okay, it's fixed. Always your dA is what? R dr d theta. And remember that you'll be having a function of what? Your x and y. Then remember your x is what? R cos theta, and your y is what? R sin theta from polar coordinates. Your R sin theta. Okay. Then you bring your what? R dr theta. So this is the whole algorithm for double integral and polar coordinates. You have your outer being the theta, your R1 to R2, a function of R cos theta, R sin theta, R dr dt. R dr. If you forget this R, you are wrong. It's not dr d theta, R dr theta. You get to understand this theta, which I'm looking for a problem for us to solve beautiful. And okay. Okay, so let's solve example. Good. So, problem. Okay. So now, one thing you should know is theta is always lying between 0 and what? 2 pi. It's very necessary. Theta is lying between 0 and what? 2 pi. So let's solve this, for example. Okay. So evaluate the integral over the region D 2xy dA, where D is the portion of the region between the circles of radius 2 and radius 5, centered at the origin that lies in the first quadrant. Good. So we have this double integral over region D 2xy dA. The D is the portion of the region between the circles of radius 2 and what? Radius 5, centered at the origin that lies in the first quadrant. What do we mean? In the first quadrant, you realize that what? Our angle was span. So now you are dealing with circles, okay? Once you hear first quadrant, you know that your angle theta will lie between what? 0 to what? 90. That's pi on 2. Okay, your R2 is radius of what? 2 and radius of what? 5, right? Therefore, my integral now, as I said, theta is always out. 0 pi on 2 integral from 2 to 5. My expression, wherever you see x, you put what? R cos theta. So 2 R cos theta multiplying what? R sine theta. Is that not it? Then your R d theta follows. As simple as that. Once you do this, you are almost done. So integral 0 to pi on 2, you simplify 2 to 5. Now I get 2. Remember 2 cos theta sine theta is what? Sine 2 theta. Is that not it? So we simply have R sine 2 theta. As simple as that. R d theta. Then my R and my R become R squared. So integral 0 to pi on 2, integral 2 to 5, R squared sine 2 theta. As simple as that. Okay. So here at first, what are you doing? We are integrating with respect to r. That's why you have r dr dt. So now it's the r d theta, right? Integrating with respect to r, I get r cubed over 3. Then I'll put in my 2 and 5. What do I get? 1, 5 to the power cube is 125 over 3 minus what? 8 over 3, right? Then what's the answer? 125 minus 8. So 125 minus 8 is 117. So divided by 3 is 39. We are going to have the whole computation to give us 39. Then I'll have my integral from 0 to pi on 2, 39 theta. As simple as that. Here I'll get 39 theta from 0 to pi on 2, 39 multiplying pi on 2 minus 0, which gives us 39 pi, 39 pi on 2. As simple as that. So it's not difficult. Just follow the algorithm and solve more problems for you to understand the concepts far better. And that covers everything under what you call double integral. So in our next meeting, we'll look at triple integrals. And also don't forget to subscribe if you haven't done so. And don't you can't afford to miss any of this.